In this class, we're going to focus on the ramifications of the fact that in quantum mechanics, we will have particles that are indistinguishable from one another, or particles that would be called identical particles. Once we have the core ideas of the ramifications of identical particles, then we can proceed to try to understand the properties of multi-electron atoms. So far, all we have dealt with has been single electrons or single particles in systems. Now we'll begin to worry about multiple particles. So this begins to bring us closer to real atoms, molecules, and solid state physics. The references for this segment of the course, I would say that Townsend is probably the best reference to start with at this level in the course. And if you are very interested in the consequences of identical particles, then reading on in the chapter that I've supplied to you out of the textbook by French and Taylor. So that's in your supplementary material if you're very interested in that. And then when we come to actually understanding the properties of atoms, Crane is a good source. So our two textbooks recommended for the course are Townsend and Crane. This is a good place to start. For identical particles, Townsend is the best place to start. Why are we doing this at this point? Well, so far in quantum physics, we have been working with completely ideal systems, and real behavior of atoms is not necessarily easy to solve in closed form, and at the least, we've got to consider interactions between electrons in systems. So we will need to take into account the fact that we have indistinguishable particles, and that will profoundly affect the nature of the wave functions that we then use for calculations. Um, in quantum mechanics, we construct a wave function for a system, and that wave function for the system will include all of the wave functions for each of the particles in the system. And somehow we've got to put all those wave functions together in order to understand what is going on. This will lead to the Pauli exclusion principle, which is stated as no two electrons in the same system can be in the same state. These effects lead to profound changes, that's what I've said, and now we'll look at how this affects the properties of atoms, or later we'll look at how this affects the properties of atoms. And of course, this is one of my themes for this course, it is not possible to calculate properties of multi-particle systems in closed form. We can understand trends and overall behavior using closed form solutions and then making approximation arguments. But in order to actually do calculations, in order to actually calculate the energy of multi-particle systems, we need numerical computation. The computational approaches go by names such as Hartree-Fock theory and density functional theory. Currently, density functional theory is the most heavily utilized theory in molecular chemistry and solid state physics. Several members of our faculty are very active in the development and use of density functional theory. So what's our plan? We're going to study the most basic wave functions and energies for non-interacting particles and non-identical particles to start out with. Then we'll proceed to start adding levels of reality, let's say. The next consideration would be to consider what happens if we have identical particles in the system. And I'll talk about what assumptions we need to make for that. If we want to solve something as simple as the helium atom, then we have to worry about the fact that the two electrons in the system interact with each other, and via Coulomb interaction at the very least, and as a result, the wave functions that we might find if we assumed that they did not interact with each other will have to be corrected. And we'll talk in general about approaches to solving multi-electron atoms. And then finally, this will be in the next class, we'll talk about the systematics of multi-electron atoms. In fact, the behavior that is observed in the periodic table in terms of ionization energies and X-ray emission lines, and the way that atoms interact with one another, basically chemistry. All right, so let's think about what happens when we have two non-identical particles. When they interact, so I've got a teal particle and a dot particle here. So 1 and 2, particle 1 and 2. So what I've got here is a movie. Time 1, slight time later, little later, little later, little later, 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 later. Okay, a little movie. So particle 1 starts here, and then short time later it is moved a little bit to the right. Short time later it's moved further to the right. It bounces off the wall, moves along like so, continues to move, and then something happens here, and now it's traveling in the other direction. So looking down here, particle 1 does something like this. Starts here, moves to here, bounces, comes up here, interacts with particle 2, and then bounces out. All right? So particle 1 follows a trajectory that we can follow. In quantum mechanics, we might not have a precise trajectory, but we can calculate what the wave function of particle 1 would be under the various interactions that it goes through as a propagating wave function. And particle 2, in this case, starts here, moves along in time, is moving more slowly apparently, interacts here, and bounces off. So we can follow particle 1 and particle 2. And we can write a wave function for each moment in time here, and then look at the time evolution, by assuming that the wave function is the product of the individual particle wave functions. That is, the wave function for the whole system is the product of the wave functions for each of the particles separately. So it's just like a product solution. We assume it, and then we look to see whether quantum mechanical solutions are consistent with reality. Okay, this is a pretty math-heavy page, but most of it is stuff that is familiar to you. We have two non-identical particles of mass 1 and mass 2. They are in positions x1 and x2, measured on the same coordinate system. So x1 and x2 are each measured as the positions of particles in a particular coordinate system. And they experience perhaps different potentials, right? Maybe they have different charges. So even though the electric field is the same for both of them, they will have different potentials due to their different charges, for example. But we're assuming at this point that they're not interacting with each other. So we can write our total energy. Kinetic energy and potential energy. Kinetic and potential for particle 1, for particle 2, equals the total energy of the system. And then we convert those classical quantities into operators. And we now have a Schrödinger equation that describes the combined system of particle 1 and particle 2. And the wave function in here is that product wave function. So the justification for guessing a product is that the variables that we're actually using to measure here are independent of one another. So we guess that the system wave function is equal to wave function A to describe the first particle, and that's the wave function is a function of position 1. wave function b to describe the second particle as a function of position 2, and a time-dependent term. Substituting that in up here, we do our standard separation of variables thing. And on one side, we've got space variables. On the other side, we've got time. And so we are going to set both sides equal to a constant. And we choose the letter E as the constant. Oddly enough, it's the same as that energy there. And so we'll use energy as the constant. And we can solve the time-dependent portion, right? And find an oscillating result. Then we proceed to separate variables again. I put all the terms that are functions of x1 on one side of the equation, and all the terms that are functions of x2, and we put the constant on the other side of the equation. In order for that to be true, both sides have to be equal to a constant. We set that to EA because if I look at this here, this is the Schrodinger equation for wave function A, particle 1 in wave function A, all right? Corresponds to energy in wave function A. And then we look at this term here, and we find that this side of this Schrodinger equation is equal to E minus EA, or we'll call that EB, all right? And we've just solved the Schrodinger equation for particle B, particle 2 in wave function B, all right? Remember, wave function, the letter for the wave function describes what kind of state the particle is in, and the 1 and 2 describes which of the two particles we are talking about. Okay, so now we have actually solved this problem. Our wave function looks like this, where my total wave function is a product wave function. The wave function for each of the individual particles is found by solving the Schrodinger equation for the potential that applies to that particle. And the total energy of the system is the energy of particle A plus the energy of particle B. So we've actually just done something that you would have guessed anyway, but we went through it in a formal approach. But there's one more step here that is not necessarily so simply intuitive. And that is that the probability, which I'll call dP, of finding particle 1 in region dx1 and particle 2 at the same time in region dx2, all right? Not necessarily the same x's, right? But in some little region of space, that probability is the product of the two probabilities, right? It is, that's what I've got over here. But more formally, dP is the probability density for the system squared, dx1, dx2. There's my volume, for example. I've done all of this in one dimension, but you can think of this as being a volume. And that is the probability of finding particle A in region dx1 times the probability of finding particle B in dx2. And that's just what we would expect if the particles were independent of one another. But when we get to identical particles, it's going to be a little bit more interesting. Okay, here's the same figure almost that I showed you before, figures from French and Taylor. But let's consider if we have two identical particles. And let's look down here. I've got particle 1, which originally we identified as going through this sort of Z-shaped path. But if the particles are identical, how do we know that particle 1 didn't execute this path here, come into some close interaction with particle 2, then go out that way. And particle 2 came in and scattered out. We don't know which of these events was actually what happened. Was it a backscattering event or was it a forward scattering event that occurred here? All we know is that we found a particle here. We started with a particle here and a particle, think about it, here. And we ended up with a particle here and a particle there. And because the two particles are both electrons and can't be labeled in any way, all we know is that an electron ended up here and an electron ended up there. All right, but quantum mechanics tells us that the probability density should be identical if I switch the two particles with one another at any point in time, actually. So the probability density for particle 1 in wave function A and particle 2 in wave function B had better be the same as particle 2 in wave function A and particle 1 in wave function B. So here's a funny way of plotting that probability distribution. Right? The simple product wave function. Now what we can do is plot the probability density for particle 1 being at position, particle 1 being in some position x1 while it's in state A, and particle 2 being in position x2 while in state B, and then switching particle 2 for 1. So this is x1 here, position of particle 1, position of particle 2, all right? So this is not your standard xy axis. This is position in x of particle 1, position in x of particle 2. And for one state, particle 1 in wave function A, particle 2 in wave function B, that product wave function, for the simple case of just taking wave functions for particles in a box, all right, one-dimensional box, that product wave function looks like this. And when we plot it, it looks like this. Maximum probability here and here, and lower probability out in this region here. Okay? And if I switch particle 2 for particle 1 in the system, my probability distribution in x1, x2 looks different, all right? It has switched axes here, and the probability distribution is different, right? However, those probabilities should be the same. How do we make the probability distributions be such that in this plot of x1, x2, position of particle 1, particle 2, it doesn't matter what happens when we switch the particles with one another. We exchange them with one another. So we want to construct a probability density that doesn't change under particle exchange. And here's a good example. This is called the symmetric wave function. And it is constructed by taking particle 1 in wave function A, particle 2 in wave function B, and then switching them 2 for 1, so 1, 2, 2, 1, switching them, and adding that switch to the original one, all right? Under exchange of particles 1 and 2, if I change the labels 1 and 2 here, 1 and 2 there, I will get the same wave function back again. And on that x1, x2 plot, that looks like this. All right, let me talk about the other possibility. This will produce the same probability distribution as well after exchange. It's called the antisymmetric state. And particle 1 in wave function A, particle 2, wave function B, and then I subtract the switch state where I've put 2 in A and 1 in B. Okay, minus. And when I accomplish this change here, what happens is I change the sign of the wave function, psi sub A. So for psi sub S, when I switch particles 1 for 2 in here, I get the same wave function back, exactly the same wave function back. In the case here, when I switch 1 for 2, I get minus, I get negative, the wave function back again. But remember, when we square these wave functions, that's the probability of what we see, then it doesn't matter if the new wave function after switching is negative or not, because the negative will disappear in the square, will be negated, right? Now let's look at this situation. Remember, this is for particle 1 at some position and particle 2 at another position, and we've created an exchange wave function that is symmetric under exchange. That is, we get the same wave function back again. And we notice that the highest probability density occurs along the line where x1 is equal to x2. Position of particle 1 is equal to the position of particle 2. That means that in the symmetric state, two quantum mechanical particles behave as though they're attracted to one another because they're along a line where x1 is equal to x2. There's no actual force between them, but if they're in the symmetric state, they behave as though they're attracted to one another. We observe them to be as though they're attracted to one another. In the antisymmetric state, where the sign of the wave function changes under exchange of the two particles, then when we make the plot of the joint positions of the two particles, probability of finding the particle somewhere, right? Square this and look at the probabilities. We find that when x1 is large, x2 is small. When x1 is small, x2 is large. That is, that on the average, particles spend more time away from one another than close to one another. Here they're close to one another. x1 is small, x2 is small, x1 is large, x2 is large. Over here it's large, small, small, large. So they behave as though they're repelling one another. Even though there's no force between them, if they are in these states, then they behave as though they're repelling from one another. Their energies don't change, but they behave in that way. If we want to worry about putting together three identical particles and to make them have the same wave function after we exchange them round robin for one another, then the way to construct a symmetric wave function would be to add up all the possibilities of putting particle 1, 2, and 3 in wave functions alpha, beta, gamma. All right, all the permutations. We want to make the antisymmetric so that when we exchange the particles with one another in any way, we switch the sign, then we end up with a antisymmetric combination of wave functions that look like this. In each case, we have 6 terms, but it's what happens when we switch two particles with one another. Now, this looks horribly messy, and your next question would be, oh, what happens when we've got 4? How do we do that? And a partial answer to that is on the next slide. A shorthand way of writing the the way to combine wave functions with one another is to construct a matrix of particle 1, 2, 3 in states alpha, beta, gamma. So 1, 2, 3, alpha, beta, gamma. And then take the determinant of that. When we take the determinant, we'll have minus signs for certain terms and plus signs for other terms. And when we are finished taking the determinant, we have constructed the antisymmetric wave function. And then to make the symmetric wave function, we just switch all the minus signs to plus signs in the determinant after we've taken the determinant. And this works for larger dimensionality. Still complicated, but easier to remember, at least. And easier to remember that we're talking about what's called the Slater determinant. So, what we know is that quantum mechanics tells us that when we square these wave functions, either a symmetric or an antisymmetric under-exchange wave function, we get a certain probability density. And then the question is, which choice, symmetric or antisymmetric, does nature actually take, or does it care? Can in a quantum mechanical system, can we just have both? And the first answer is no. You can't have both for any particular type of particle in a system. The answer that nature gives us under exchange is for indistinguishable particles that under exchange, sometimes the wave function will switch sign and sometimes it will not switch sign, right? But it depends upon the type of particle. And before we proceed, I need to talk about another property of particles. We have introduced it previously. We've introduced the idea of spin. In particle physics, there are other properties of particles that we might have to pay attention to. I've got some of them listed here. We're just going to worry about the spin of particle for now. And just as a point, I will tell you that electrons have spin 1/2, that you knew. Photons, we actually gathered from our transitions calculations, have spin of 1, or angular momentum of 1. And other particles, like a helium nucleus, for example, turn out to have spin of 0. So different types of particles have different spins. So how do we characterize that? How should we think about this? We apply a magnetic field. We know spin 1/2 particles can be in a spin up or spin down state with respect to the axis of the magnetic field. And if we have two particles, we can put both particles into spin up, one up, one down, one down, one up, and both down, all right? The first state, up, up, and the last state, down, 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 are symmetric within themselves. So if I took my two particles and put them both into a spin up state, then when I switch them, the wave function doesn't change. Similarly, if they're both in a spin down state, when I exchange them, the wave function doesn't change. But when I have a combination, up, down, down, up, then we can ask, how do I combine those in order to make symmetric and antisymmetric states? In symmetric, we put, let's say, up, particle 1 up, particle 2 down, and particle 2 up, particle 1 down. Add them together in this way, and then under exchange, we get the same combination back again. And if I put a minus sign in here, when I exchange 2 for 1, then the antisymmetric wave function is minus the symmetric wave function. because we're going to need to keep track, and later on it's harder to make these arrows, I'm going to call the spin up state the alpha state and the down state the beta state. So the symmetric state, all right, the symmetric state up here consists of alpha 1, alpha 2, both particles in spin up, up, up. In that case, the spin projection on the z-axis is +1. I can have beta beta, that is down down, and spin projection is -1. And then I've got this combination of up down plus down up. Oh, sorry, yeah, plus down up. Let me put it that way. Which these two spins cancel one another, and as a result, the total spin for the system is 0, right? But we've combined two particles in order to make that 0 spin. And all three of these possible combinations are symmetric under exchange. That is, you get the same sign back for the wave function after you exchange them. And the other combination with the minus sign is anti-symmetric under exchange. That is, it switches sign. And once again, because it's up, down, down, up, the total spin of the system is 0. This, because there are 3 of these, is called a triplet state. And this, because there's only one of them, is called a singlet state. So the total wave function for the two particles in our system is the product of one of the possible spatial wave functions that we talked about, maybe the symmetric or the antisymmetric, and one of the possible spin wave functions, symmetric or antisymmetric. If I have symmetric, symmetric, the product is symmetric. If I have symmetric, antisymmetric, the product is antisymmetric. Remember, antisymmetric and symmetric mean that the sign switches when we exchange the particles. And if I have anti-anti, then I end up with symmetric under overall exchange. This is the overall symmetry, and that's the symmetry that turns out to be important for the behavior of systems. And the behavior of systems I'm going to describe in a moment for fermions as the Pauli exclusion principle. So as far as we know, there are 2 types of fundamental particles. There are particles with half-integer intrinsic spin, and we call those fermions after Enrico Fermi. And those wave functions for fermions has to be antisymmetric with respect to exchange of identical particles. Examples of fermions are electrons, muons, protons, neutrons, and many atomic nuclei. Particles that have integer spin are called bosons after Bose, and they are symmetric with respect to exchange of the identical particles. And examples of those include photons, pi mesons, alpha particles, which is the nucleus of helium, and the actual whole helium-4 atom. And this behavior follows from the solution of the relativistic Schrodinger equation, which was done in the, I can't remember exactly when, and the date is here, by Wolfgang Pauli. And so he showed fundamentally, using theoretical considerations, that we expect that particles with half-integer spin will be antisymmetric under exchange, and particles with integer spin will be symmetric under exchange. And these are the 2 behaviors that we have observed experimentally. The Pauli exclusion principle, the one that you learned about in chemistry, is a consequence of the anti-symmetry requirement. And in class on Tuesday, we are going to go through an activity in which you are going to show that the wave function amplitude for two electrons that happen to be in the same anti-symmetric spatial state is 0. Okay, so we've done that activity now, and we can talk about the consequences. The Pauli exclusion principle tells us that we can't put more than 2 electrons into a single spatial state. Those 2 electrons can have spin up, spin down, and the spin portion of the wave function has got to be anti-symmetric if they're in the same spatial state. And then in addition, this idea, the fact that if particles are in a space symmetric state, they are on the average are closer to one another. And if they're in a space anti-symmetric state, on the average they're further from one another, can lead to corrections to the energies when the particles interact with one another. For example, electrons in a helium atom or in any atom actually repel one another. They're attracted to the nucleus, but the electrons repel one another. And if on average they spend time further apart, then their binding energy will be higher. So we're going to work through, in this class, one example. And this is as simple as it gets. And we can do this problem numerically. In this class, we actually can, but it's somewhat involved, so I'm not going to require you to actually do this. I'll just show you some of the results. All right. So you proved a few slides ago, right, that 2 particles with anti-symmetric exchange symmetry can't be in the same state. And therefore, we can only put 2 electrons in the ground state of helium. Spin up, spin down. That makes them different states. We'll approach this problem in, let's say, a variety of different approximate approaches, ranging from the simplest, which gives sort of poor energy agreement, but gets the order of magnitude right, through to excellent, where in the level of approximation, we're talking about much better than 1 part in 1,000 energy calculation. And doing things carefully and relativistically allow us to calculate these energies to better than 1 part in a million with current theories. Okay, so first what we're going to do is ignore everything that we've just done and solve for the helium-4 atom. That's 2 electrons, remember, 4 nucleons and 2 electrons, as though the electrons don't interact with one another, and as though the electrons are distinguishable from one another. That's what we did in the very first slides of this lecture. Our wave function then is the product wave function, and the solution is Schrodinger equation for particle A, for particle 1, Schrodinger equation for particle 2 in wave function A and wave function B. And initially, we're going to assume that both particles are allowed to be in the ground state of the system, and we're ignoring the interaction. So the potential here is just a Coulomb potential with a nuclear charge of 2. Because these 2 are independent of one another, we can solve for the wave functions and the energies for each of these separately, and then add them together to get the total energy. for one particle, particle 1 in state A, all right, we find the ground state, and we find that its energy is what we would have found for a hydrogenic situation. We just put a z squared in there. Everything else is the hydrogen equation. And so the binding energy for particle 1 in state A is 4 times the binding energy for electron on proton, Rydberg energy, which is 54.4 electron volts. I've got 2 of these, so the ground state energy for the system is 2 times 54.4, which is a binding energy for both electrons in the system of 108.8 electron volts. Actual experiment is 79 electron volts. All right. If we wanted to actually make a prediction on whether chemistry would happen or not, would this react with something? This would be a horrible approximation, because chemical interactions depend upon being able to calculate energies to within tenths of electron volts. And we're off here by, I don't know, 40. Not so good. Oh, maybe only 30 electron volts off. But you can't predict chemistry based upon 30 electron volt errors. Right? The first excited state, if I put an electron in the n equals 1 orbital and another one in the n equals 2 orbital, yields a total binding energy of a system in this approximation of 68 electron volt. Oh, sorry, I take it back. Of 40.8 electron volts in this theory, and the actual binding energy is 68 electron volts. So off by 20, not good. So the next step would be to say, oh, we ignored the interactions between these 2 electrons. Let us go ahead and solve the problem as 2 independent electrons, and then correct the energy for the system by looking at the Coulomb interaction between the 2 electrons, from which we want to know what the average separation between the 2 electrons is. Right? So we just go ahead and put both electrons in the n equals 1 state, and we treat them in that state as though there's the final state, right? And we treat them in that state as though they, on the average, are some distance from one another. So what we need to do to put in here is to correct for that Coulomb energy. So we need to find the average of 1 over the position of particle 1 minus the position of particle 2. So we have a full vector position in there. And in order to do that, we take our wave function in R1 and R2, and we integrate over all the possible distances between the 2 particles, given the shape of the wave function. Wave function squared, that's a probability density there. We can then, for example, just take R1 along one axis and then calculate the distance between the 2 particles based upon assuming R1 to be in a particular direction. So then our integrals become integrals in angle. This integral is done for us, and it turns out that 1 over the distance between the 2 particles averaged turns out to be 5/4 of 1 over the Bohr radius, right? So the average distance between the 2 is something like 80% of the Bohr radius, right? So the energy difference, the correction to the energy due to electron-electron repulsion is electron energy squared over 4 pi epsilon naught average distance between the 2. It's a correction of 34 electron volts. So the ground state now comes out to be 74.8 electron volts, where remember the experimental value is 79. So we're only off by 5, but that's still not good enough to actually make chemistry predictions. So we want to do better. And we've ignored everything that I started with in this lecture. So let's take a look at better ways to include the electron Coulomb interaction. The traditional approach and the most straightforward approach is called the Hartree-Fock approximation, or the Hartree-Fock approach. The way that we proceed here is to just go ahead with our helium nucleus and calculate the wave function for one electron, ignoring the other electron. It's not there yet. We just put one electron into the system. But then we use the wave function for that first electron that we just solved for to find a charge density. And given the charge density, we find the potential for the system of the nucleus and that one electron that a second electron coming into the system would see. So we use that wave function and the nucleus to provide a potential, and then we solve for the wave function of the second electron by a numerical integration technique. All right? Now that's not going to be right, because that second electron coming in is actually going to influence the first electron. But it's a step in, let's call it, the right direction. Then what we do is to use the wave function from that second electron that we just calculated, plus the nucleus, as the potential to resolve for the first one. So go back and solve the first wave function again, given the presence of the second one. And that provides a correction now to the wave function for the first electron. Then take the wave function from the first electron, use it for the potential to calculate the second electron again, and go through that process iteratively until the energy in the system stops changing. This process will produce an accurate energy and and the wave functions for this system. Okay, we have as yet, by the way, ignored the imposition of exchange symmetry on this system. But so far, we've got an approach. This is called the Hartree-Fock approach. As a little comment here in class, ask me about what Hartree's father did. I'm going to skip this. It's in the slides, and I think that it's cute, but I'm not going to talk about it. So this Hartree approach also gives us some other energies, but I'll talk through this. It gives us the binding energy of both electrons when both electrons are in the n equals 1, L equals 0. Remember, they have to be in spin up and spin down states. They have to be in different spin states in order for this to happen. But we can, according to our initial symmetric, antisymmetric arguments, put two electrons into the ground state. When we do that and make that correction, not just correction, and calculate the wave functions, including the interaction between the electrons in the form of one electron forming the potential for the other electron, we find a total binding energy of 79 electron volts. That is really close to the experimental number. So this worked pretty well. This approach as well gives us some idea of what would happen for excited states. What's the total binding energy of an electron in the ground state plus a second electron in the n equals 2, L equals 0 state. The binding energy there is 59 electron volts by the Hartree method. And for the n equals 1, L equals 0, and combined with the second electron in n equals 2, L equals 1 state, the binding energy is a little bit less. So what's the idea here? It's that, well, actually what is shown here are the actual wave functions, shape of the wave function, for a pair of electrons in the 1s orbital, right? But to compare to it, we'll put what the wave function would look like for a hydrogen, for an electron on a nuclear charge of 1. So electron on a nuclear charge of 2, electron on a nuclear charge of 1. And so a way to think about this in the Hartree-Fock method is that we put our first electron here because it sees a nuclear charge of 2. The second electron looks at the overall system and from out here sees a nuclear charge of 1. And so its wave function is sort of out here going to look like the wave function for a electron on a hydrogen nucleus, effective charge of 1. In here it will be distorted because there's some probability that this electron here sits inside the orbit of this electron here. So this electron will see a distorted potential due to the presence of the distribution for the first electron. And then now we've calculated this one here. Given this one, we calculated that one. Now that we've got this distribution, this second electron spends some time inside the orbital of the first electron, lowering its potential interaction with the nucleus and causing the wave function for the first electron to move out. And then when that happens, the second electron is actually seeing more of the nucleus and it moves in. So these two end up converging upon one another into one final state, which sits somewhere over here, right? When we think about excited states, then in the n equals 2, L equals 0 state, the probability distribution for that electron looking at the original electron on the nucleus, right? The first one is in this state here, all right? Then the second electron looks at that and sees a charge of 1 and goes into an appropriate state for a nuclear charge of 1. And only a small fraction of this nuclear charge, of this electron, ends up inside the orbital of the first electron. So the distortion that this one causes on that one is relatively small. However, if I'm in the n equals 2, L equals 1 state, then it turns out that the charge distribution for the second electron is now going to be pushed in because that state has just got one lobe and it's a little bit further in, and therefore the second electron will do a better job of screening the first electron from the nucleus. And so we can make guesses, not actually do a closed form calculation, but we can make guesses as to how the binding energies are going to change. Here's what I was talking about a moment ago, that in the n equals 2, L equals 0 state, the electron spends most of its time out here with only a little bit in here. In the n equals 2, L equals 1 state, on the average, the second electron is in closer to the nucleus. And therefore, that changes the binding energy for the various systems through charge penetration into the orbit of the other electron. Now, from the start, we were talking about exchange, and so now we can worry about the exchange interaction. What happens when we require that the pair of electrons be in a space symmetric state or a space anti-symmetric state? Remember that for our pair of electrons, the entire wave function has to be anti-symmetric. So if the spin state is symmetric, then the space state has to be anti-symmetric, and the only way that that can be is when the two electrons are in different space states, right? And when the spin state is anti-symmetric, the space state is symmetric. That relationship, that idea, tells us that for different possible spins, we'll end up with different binding energies for the system, slightly different binding energies. The anti-symmetric space state results in the electrons on the average being farther away from one another, and so their repulsion energy is lower. That means that in order to put something into an anti-symmetric space state, we had to put it into a symmetric spin state. Two spins the same. And that means that if we lower the Coulomb energy by putting two electrons into an anti-symmetric space state, then the spins will, on the average, be in the same direction. Now, for two electrons that are in the same space state, let's say the n equals 1 space state, their spins have got to be opposite to one another, that they have to be in an anti-symmetric spin state. But if the two electrons are in different space states, n equals 1, n equals 2, then on the average, they will want to be in the same spin state. Energetically, that will be preferred. And that explains why in chemistry, when people start filling orbitals, let's say you're talking about the 2p orbitals, when they draw the electrons in, they put the electrons in spin up, spin up, spin up, because you've now put them into a spin symmetric state, which allows them to be in a space anti-symmetric state, which means they're further apart on the average, so their repulsion is less. So here's a schematic of what happens. The scale here is not quite right, but this will give you an idea. In the very gross non-interacting particles approximation, our two electrons in the n equals 1 state have a binding energy of 109 electron volts, which is incorrect. So this is the approximation where we ignore the interaction between electrons for the ground state and for the first excited state, n equals 1, n equals 2. And if we include the interaction between the electrons and do a Hartree-Fock calculation of the wave functions, allowing the interactions of the electrons to dictate the new wave functions and doing it iteratively, then the energy for the ground state comes out pretty much right on. And because these have got to be in the spin up, spin down, anti-symmetric state, that state is a singlet. There's only one of them, and the energy doesn't get shifted at all by the symmetry. Right. Now, for the excited state, I have one electron in the ground state and one electron in the ground state and one electron in the excited state. But the angular momentum in the excited state can be different. And we find that for a higher angular momentum, the binding energy is different than for low angular momentum state. And this has to do with the shape of the wave function for each of those and the extent to which the second electron wave function penetrates within the first electron wave function. So that's what gives rise to the difference there. And then if we look at the total symmetry of the state, we find that for different spins, the interaction between the electrons changes because the space wave function is forced into a symmetric or antisymmetric space wave function. So we get the next level of correction from that. Again, these corrections are, let's say, exaggerated. The scale is not quite right. And then just a little hint for what's coming in the next class. The overall pattern of the periodic table can be deduced from thinking about hydrogenic orbitals, electron-electron screening, that is, the fact that one electron can sit inside the orbital of another electron, and the fact that we're only allowed to fill up our space states in certain ways due to the Pauli exclusion principle and the fact that wave functions under exchange must be antisymmetric. So we will be talking about that in the next class.